Recording in progress.
Yeah, come on everyone, let's start off. There, so this was the last thing that we're doing, the escape velocity. Chalo, others keep your camp on. Great, so let's go ahead. And let's start off with a question. So we have two planets here. Density are rho and radius is r, and we have another planet here. Density is 2 rho and radius is 2 r. Find ratio of g on the surface and find ratio of escape velocity. Two questions. So we have two planets of radius rho and r. And second planet density is double, radius is also double. So on these two planets, find the ratio of gravity, that's small g, and find the ratio of v escape velocity. Get it? It's simple, just a formula-based one. Try. I'll give another 45. I'll give a minute more. Let's see. Straightforward formula substitution, there's nothing there. So first thing, if you look at g is nothing but gm by r square. But here mass is not given, density is given. So replace mass with density, which is a rho into 4 by 3 pi r cube by r square. So g is proportional to rho into r. . Therefore, G1 by G2 will be rho into R by 2 rho into 2R. 1:4. V escape is root over 2gm by R. Again, mass is not given. What is given is density. So convert mass into density. 2g mass will be rho 4 by 3 pi R cube by R. So we can see V escape is proportional to root rho into R. That is R square that comes out. So V1 by V2 will be root rho into R by root 2 rho into 2R. 1 by 2 root 2. Clear this? There, straightforward substitution there, nothing much. Any doubts on this? Next thing. Now, just to give a little brief, if you see how they did the derivation of the satellite, uh, simply this is what we said. We said a particle is going in a circle, so the gravitational force and the centrifugal force are balancing out. So we got gm by r square is mv square by r, and from there we got velocity. Once we got velocity, we said time period is the circumference 2 pi r by velocity. We got the time period. And once we got this, then we said for the energy part, the potential energy is g m1 m2 by r, and the kinetic energy is half mv square, and we already calculated. So we got kinetic energy. When we added them, we got the total energy. Isn't this what we did the derivation? Clear with the derivation. So it all started with one simple thing here. The gravitational force is equal to centrifugal force. And once you got velocity, you got everything else. This is how we did the derivation. Now, every time exam, they won't ask you questions like this. Question should be something of this sort. So let's see what will happen if they mess up the whole thing. So let's say the force between the satellite and the planet is given by F is equal to minus C by R power N. C is some constant. Minus indicates attractive force. R is the distance from center of the planet. M is the mass of the satellite. N is some number. N could be any number. So the regular gravity, right, that N used to be 2, isn't it? So exam they can ask like this. The force is equal to minus C by R power 2.5. Then find the velocity and find the time period. You're getting it? So every time it need not be R squared. You create a hypothetical situation. So find velocity as function of N. Find time period as function of N. So if they ask you velocity and time period, this will be a proper mains level question. Find the total energy. Now this question suddenly goes into advanced. And value of N for a stable orbit. You can't take whatever value you want for N. There are certain values which are, if you go beyond those values, right, what will happen? The satellite won't be in a stable orbit. It will fly off. Value of N for stable orbit. Now if I ask you total energy and value of N, suddenly it becomes an advanced question. It would be a good paragraph question. Let's do this. Think about it. Then I'll give you a minute or two, and then I'll explain a little more. Then I'll give you a little more time. But I hope you got the question. Every time it won't be 1 by R square. Get the first two parts; those are manageable. Hmm. Yeah, you get something of that sort. R power n minus 1 by 2 or something. Let's see. The first part is fine. So the force of attraction F and the centrifugal force will be mv square by r. So the minus indicates attraction. So I just showed it in this thing. So g c by r power n is mv square by r. That's straightforward. There's nothing there. So c by m r to the power of n minus 1 whole to the power of r. The time period will be 2 pi r by v. 2 pi r. This is r by v will be root over c by m 1 by r power n minus 1 by 2. It goes up. 2 pi root over m by c r power n plus 1 by 2. There, that's your time period. What about total energy? And what do you mean by a stable orbit? Now, if you go back to the definition of a satellite, we wrote this thing. An object that revolves around a planet in a stable orbit. What is a stable orbit? It's a bounded orbit, a closed orbit, or the total energy is negative. That is a catch. So you need to find the values of n such that the total energy is negative. Think about it. If total energy is zero, means what? The planet and the satellite got separated to infinity, right? When does the gravitation energy become zero? When the two particles are at infinite distance. Means they got separated forever. So if you want the system to be a stable orbit or the satellite to be bounded, the energy has to be negative. So this is the meaning of this. So stable orbit implies total energy of the satellite is negative. Now let's find the total energy. So once you got the total energy, then it is just a matter of putting less than zero, and then you'll get n value. So total energy and n are related. This would be a good question. It could be a good more than one choice question. Now in the energy, right, there are two parts. There's a kinetic energy and there's a potential energy. Kinetic energy is easy. Half mv square. So this is m by 2 c by m, and this is r power n minus 1. So this will be c by 2 into r power n minus 1. But how do you find potential energy? Now, this is a mistake people do. There is not only kinetic energy, right? If there is an interaction between two objects, there will be a potential energy. Now, is there any relation between force and potential energy? There is. So listen carefully. This was the trap in the whole question, actually. So we know F is equal to minus C by R power N, and we know F is also equal to minus du by dr. So integrate on both sides. So we will get du is equal to C by dr by R power N. Integrate on both sides. Now, this is the thing. So the limits will go from R to infinity or infinity to R. Why infinity? Because remember, we take infinity as a reference line. At infinity, the potential energy is 0. So this guy will be u of infinity to u of r. So when you integrate this on both the sides, you will get u of r minus u of infinity will be c by, that is r power minus n. So 1 minus n into r power 1 minus n. Limits will go from infinity to r. So this will be r by 1 minus n and minus infinity 1 minus n. Now we choose infinity as a reference. A simple reason why infinite is reference, because at infinite distance there's an interaction between them, so we can say the energy is 0. So u of infinity must be 0. Now that means this second term here, this has to be 0. This is 0. This has to be 0. Now think about it. Suppose, for example, that 1 minus n becomes a positive number, then you'll get infinity to some positive number. Then this value will blow off to infinity, right? So this has to become 1 by infinity, isn't it? So 1 by n has to be 0. Therefore, 1 minus n must be negative. Is that making sense? If 1 minus n is not negative, that value won't go to 0. That value will actually blow off to infinity. So you get infinite energy. It doesn't make sense. So n must be greater than 1. This is one condition. N ka value has to be greater than 1. If n ka value is less than 1, it won't be a stable orbit. Energy will become infinity. Potential energy becomes infinity. Is this part clear, everyone? So under this condition, so the potential energy becomes, so u of r is c by 1 minus n by 1 by r power n minus 1. Now, this is valid for n greater than 1. For n less than 1, u of r will blow off to infinity, so the energy won't be defined. You can say u of r becomes undefined. So we should not take those values because it won't be a stable orbit. It won't be a satellite. Then you can't call it a satellite anymore. Infinity per 0 is undefined. Is this the first part, everyone? Is this getting even clear? It's the most common mistake. People forget the potential energy part. So that's your potential energy. And we have our kinetic energy. So the total energy will be potential plus kinetic. If you see, this is actually the same derivation which we did in the gmm by r square also. I just kept r power n, so it looks a little complex, but it is just more of a math. How much is kinetic energy? C by 2 r power n minus 1. Potential energy C by 1 minus n r power n minus 1. Same thing. So So C by R power n minus 1 will be R plus 1 by 1 minus n. This is your total energy. And now you're saying this total energy must be negative for stable orbit. Now C by R power n minus 1 is positive, and then that means the coefficient must be negative. This thing, if I just cross multiply 1 minus n plus 2 by 2 into 1 minus n less than 0, this will become 3 minus n by 1 minus n. And from inequalities, you can see either one of them has to be positive and one of them has to be negative. So if you take 3 minus n greater than 0 and 1 minus n less than 0, but I already know n must be greater than 1. If n is greater than 1, the denominator is negative. So 3 minus n must be greater than 0 and 1 minus n must be less than 0. So this will give you n less than 3 and this will give you n greater than 1. Therefore, n ka value should be between 1 and 3. So these are the limiting values. If the n ka value is exceeding 3 or less than 1, the orbits are not stable. Why can't you say total? Say na, Vehan. Who is not telling you? Say it. Then what? Did you get the answer?
So,
I don't know what you're talking to. What is TME? Total mechanical energy.
so like, why isn't
And
this?
what did I do here then? What is this thing then?
The question was that why is this insufficient? Why do we have to do that other thing with the potential energy as well?
So find how you want to find the energy. Tell me what is the answer for energy then, without doing anything. Yeah, tell me now. What is the energy then? So you're saying don't do anything. Okay, I won't do anything. So just can you tell me what is the total energy without solving anything? Yeah, please tell me. So when the force is minus C by R power n, what is the total energy? I think you can just see and tell it, right? So tell us. Please enlighten us how to get the energy without doing anything. So
So like the potential energy, why can't that be positive?
what can be positive?
Potential energy.
Fine, let it be positive. So what is the problem?
Okay, so
Is
so
kinetic energy positive or negative?
okay. Yes.
No, just this is a proper way to do it. That you will get the answer, but that means something else. But there's a kinetic energy also right here, so you can't do that. What you're saying is something else. There's a proof actually. Like if you take the particle slowly from infinity to R, it would give you the same thing, but yeah. Is this clear to everyone? So the whole problem, this is the main part there. You need to find the kinetic energy, which is always positive. That can't be negative. Potential energy has to be negative. And that will be the values there. N ka value has to be between 1 and 3. This is how the last question is in the advance. They'll not give you every time that if I give you numbers, right, your life is actually easy. So if I give n is 2.5, it still works. But if I give n is 3.3 or 4.5, you're gone. It won't be a stable orbit in the first place. So if I just ask you for the time period, this itself is a proper mains level question. Clear, everyone? So don't mug up 3 by 2 blindly without understanding, the thing. Because if the force is 1 by r square, then time period is 3 by 2. If the force is 1 by r power n, it is something else. Clear? This is how questions will be framed based on that orbit. Let's see one more. Now, every time you won't get circular orbits. Did they just teach you ellipse in class, Max? Is ellipse done? Eccentricity, A, B, you do have an idea, I suppose. Okay. Let's see. In case if you don't have an idea, I'll just still brief you a bit later on. So we have an ellipse here. So at one of the foci, there is a sun. So here the particle is going with V2. This point is B, and this is R2. This is R1. This point is A, and this is going with V1. So basically, a satellite is going in an elliptical orbit. with the sun at the focus. A is the closest point. B is the farthest point. Right. So find V1, V2 in terms of R. So I know R1 and R2. I don't know V1 and V2. Find the total energy and the angular momentum. This will be another proper advanced paragraph question. Find time period. Time period for one rotation, one complete thing. Find the radius of curvature at A and B. And if you see, these are the kind of questions, right, which we didn't do in electrostatics. Let's get this. Let's set the first part. I think once you got the first part, the other things will come fall in place. The C is the thing. The time period is a little messed up one, but yeah. I miss the mass of the sun. Try, get the velocity, but I'll give you 2 minutes. Did you get the velocity part? Let me tell you something. Meaning, this is something which I kept on telling you like a broken tape recorder. If something is not going in a straight line and something is not going in a circle, what can we do? There's only one way to do. What? Conservation of angular momentum, conservation of energy. We don't have any other technique to solve. Yeah, You can do that happy now. And then next year you can cry. It is all, fun and jokes right now, but next year once the results are out for your seniors like now, we are seeing, right, how people are thinking like they don't know what to do now. They don't know which college they'll get. Let's see. No, just that is wrong. Daksha, I think you got it. Try the remaining parts. I'll give you another 30, 40 seconds and I'll show you. Let's see. So state 1 and state 2. This is state 2 and this is state 1. Now, if you look at this, angular momentum is conserved. We have to conserve angular momentum. Great, but about which point? That's the thing you need to ask yourself every time. You just don't say angular momentum is conserved. About which point are you talking about? Now, if you look at this, the gravitational force is always passing through the sun. No matter where the planet is, the gravitational force is always towards the sun. Therefore, torque about the sun is zero. Therefore, angular momentum about sun is conserved. So the angular momentum will be mv1 r1 is equal to mv2 r2. So we have v1 r1 is equal to v2 r2. Second thing, energy is conserved. Energy in state 1 is equal to energy in state 2. Half mv1 square, kinetic energy, potential energy is minus gmm by r1. Half mv2 square minus gmm by r2. Small m cancels, take v2 and substitute here. So you'll get v1 square by 2. This will be v2 square will be v1 square r1 square by 2 into r2 square. This will be gm by 1 by r1 by 1 by r2. Technically speaking, once you write the momentum, the angular momentum and energy physics got over. It is just a matter of solving. Take out v1 square common here. This will be 2gm. Let me write it down for you. So this guy will be r2 square minus r1 square by r2 square. This will be gm into r2 minus r1 by r1 r2. There, so r2 r1 will cancel off, r2 minus r1 will cancel off, 1 r2 will cancel off. You will be left out with b1 will be root over root 2 gm r2 by r1 by r1 plus r2 curve root. There, that will be a velocity. Check. Clear? Then if you got v1, you'll get v2 also. v1 r1 is equal to v2 r2. So this will be root 2 gm r1 by r2 into r1 plus r2. There, we got velocities v1 and v2. Once you got this, you can find the angular momentum, that is L is equal to mv1 r1, or you can take mv2 r2. You'll get the same thing. So this will be m into root over 2gm r1 r2 by r1 plus r2. And for the total energy, it is half mv1 square minus gmm by r1. You could have taken half mv2 square gmm by r2 also. Substitute the values here. So this will be half mv1 square will be 2gm r2 by r1 plus r2 minus gmm by r1. Take out gmm by r1 common. We will get r2 by r1 plus r2 minus 1. This turns out to be gmm by r1 plus r2. This is your total energy of a elliptical orbit. Basically, r1 plus r2 is the major axis. I'll write this down results later on in a proper format, but that is a proof. Means it doesn't depend on the minor axis. There we got the total energy. Like I said, this thing looks big, but the moment I wrote this and I wrote this, physics got over. Have a look at the steps. Play with this. Any doubts on this? How do you find the time period? That is a little messed up. Let's see. This is a little different. Now, before directly jumping into it, we need to prove something here. So basically, this is the proof for Kepler's second law. Let's say somewhere in the middle, this is your r bar. The particle is going with some velocity v bar. So in small time, it will be v bar dt. So we get a small sector like this. In time dt, it travels v dt. Now what we got is a thin, it's like kind of a triangle where this is r bar and this is v bar dt. Anyone remember how to find the area of a triangle? If a bar and b bar are sides of a triangle, what is the area of a triangle? Vectors, people. Anyone remembers? Half a cross b. A cross b gives the area of a parallelogram. Half of a cross b will give you the area of the triangle made by the vectors a bar and b bar. So here for this thin triangle, the area will be dA bar, which is given by half. A bar is r bar and b bar is v bar dt. So if we bring dt this side, this will become dA by dt. This is half r bar cross v bar. Multiply and divide by mass. So it will become mr cross v bar by 2m. mr cross v bar is what? It's an angular momentum. This is angular momentum by 2m. And this is a constant thing. So this dA by dt is called areal velocity. This is the amount of area covered per unit time. So what this means is, we will talk more in detail in this thing. But what this thing tells you is, when the satellite is going, it covers equal amount of areas and equal amounts of time. So if you take a elliptical orbit, when the satellite is very far, it will go slower, isn't it? So let's say in 1 hour, it will go from here to here. So this will be the area. When the satellite is here, it will go very fast. In 1 hour, it will go from here to here. So this will be the area. So this statement says this area and that area are equal. Getting the meaning of this? So that radius vector will cover always equal amounts of area and equal amounts of time. If you're far, r is big, velocity is small. If you're closer, r is small, but velocity is more. So the product r cross v dt will always remain constant. So we found out that the area covered per second is constant. So from here, how will you get the time period? So what is the time period then? Do I know area of an ellipse? Therefore, the time period will be, I know the area of an ellipse, which is pi AB, by areal velocity. Area of an ellipse is pi AB. Areal velocity is L bar by 2m. So if you can substitute this, now I'll not be solving this, but these are the data things. So if you take an ellipse, if you take the center as origin, the focus will be AE comma 0. This will be A comma 0. This will be minus AE comma 0. And this is minus A comma 0. And you said this is R1 and this is R2. So from here you can clearly see R1 will be A minus AE. R2 will be A plus AE. And we also know the eccentricity ka formula E is equal to root over 1 minus B square by A square. So take all these values and substitute there and try to solve, then you'll end up. Basically, you need to eliminate B ka value and D ka value. Get everything in terms of R1 and R2. You will end up with the time period will be 2 pi root GM R1 plus R2 whole power 3 by 2. This is what you get the time period. You can check it out on your own, those calculations. So I just need to get a B ka value in terms of R1 and R2 and substitute there and my job's done. Is this clear, everyone? So the main catch is this part. You should figure out that the areal velocity is constant. And this is actually the Kepler's second law proof. We will see what is Kepler's second law, but yeah, in case you know. Any doubt on this? Okay with this? Question is still not over. We need to find the radius of curvature at A and B. Haan, Daksha.
So for the time period, actually, I can we use Kepler's third law? So like,
What is Kepler's third law?
basically, I just use the formula like.
What is the formula?
The A will be R1 plus R2 by 2. So if
Okay.
you actually cube that, then there should actually.
So what about this constant? Where is this constant? How will you get the constant?
So that is there. That's fine. So actually,
Where it is there? Where it is there? That is not the question. The question is find the time period. You can't tell me time period is proportional to R1 over per 3 by 2. I don't want proportionality. I want the time period.
Okay.
Getting it? Kepler's third law just gives you the proportionality. It doesn't give you the constant. Means you don't know the time period. You just know the proportionality.
Okay.
Is this clear, everyone? The aerial velocity is a tricky part. Now, this thing, you won't get an idea. You should have seen this before. But keep this in mind. Quite a useful thing. Now, how do you find the radius of curvature? That is kind of little easy. In circular motion, we studied what is radius of curvature. A centripetal is v square by r. So the radius of curvature is simply v square by the centripetal acceleration. Now, be careful here. So in this corner, if you take a small circle here, so this particle velocity is v2. This will be your centripetal acceleration. So AC is nothing but force, which is g m by r2 square. That will be the thing. So by mass, the attraction force by the mass of the thing will give you the acceleration. Therefore, the radius of curvature would be the speed there v2 square by gm by r2 square. And if you see by symmetry, it is also the same thing here also. You'll get the same radius of curvature here and there. This would be v1 and this would be some AC1. Radius of curvature is same, but this is how you find. So find the force acting on the satellite at that instant. Force is equal to mass into acceleration, and that acceleration is centripetal acceleration. So most common mistake, right? What people think, they think R2 is the radius of curvature. No, this is not the radius of curvature. R2 is simply the distance between the sun and the planet. Radius of curvature depends on the trajectory or the path. Is that clear, everyone? So you just find the force between the sun and the planet, divided by mass, you get the acceleration. That will be the centripetal acceleration. And v square by r, you get the radius of curvature. All clear with this? So I'll just put on the results. So if you have the ellipse here, we have the sun here. This is 2a, your major axis. This is 2b, the minor axis. And when this satellite or anything is going in this orbit, the total energy of a satellite in an elliptical orbit. Circular orbit is fine, we know that thing. That was easy to derive also. Is minus gmm by 2a. If the ellipse becomes a circle, 2a becomes 2r, right? So you get minus gmm by 2r. So circle is a very special case of an ellipse where a is equal to b. Time period t is given by 2 pi root over gm a power 3 by 2. I think this thing will come out to be r1 by r2 by 2. And that will be 2 pi root gm a by 3 by 2. Now, if you notice something here, both of them are independent of b ka value. Quite an important result. This will be direct questions. It doesn't matter what is the value of b. So there was a question like this in JE. They said a satellite is going in 3 orbits. There's a circular orbit. There is an elliptical orbit. And there is another ellipse. So it was given like this 3 orbits. And the question was, compare the energies and compare the time periods. Which satellite will have same energy more and which satellite will have more time period. It is all same. They all have same time period. They all have same energy. They will have same energy and same time period. Then what is different between them? The difference is, for the blue one, the planet is at the center, so this would be the focus of this. For the red one, the focus is somewhere here. And for the green one, the planet is somewhere here. So basically the focus shifts. For the three orbits, the position of the sun or the star is different. You're getting it? For the blue one, the is a circle, so the sun will be at the center. For the red one, F2 is the focus. For the green one, F3 is the focus. Is that making sense, everyone? So in the three cases, what is different is the position of the sun. But they have same energy and the same time period. That was a pretty good question. That would be proper mains or a bit style question. Direct question. Matlab, if you know, you can just mark it and come. Any doubts on this? Clear with this? So be careful. It doesn't depend on B, but if B becomes greater than A, that means B has become the major axis. Any doubts on this? So this is how they'll ask questions on satellite. Like if you see, this was the standard results, what we got, particle and all. And then we made it into a circular orbit, but r power n. Then we made circle ko nikal diya, and then we made it literally ellipse. And we did one thing even before also. We removed the particle and we kept a rod. Remember this question? If you think about it, this is also kind of like a satellite only, right? But instead of a particle rotating, the rod rotating. So this is actually also a satellite equation, a space elevator. So all these things will be different types of satellite questions I can ask you. Every time they won't ask you particle is going, find time period, find energy. That is standard stuff. That much you can handle it. These are the main ones. Let's see something else. We have a planet here, mass m, radius r. We have a satellite going in an orbit. Mass of the satellite is m, and this is going with u, and this distance is 3r. And then what happened? A stone of mass m by 2 with speed u by 2, it comes and hits the satellite and gets stuck. A rock of mass of m by 2 with speed u by 2 moving radially means it is coming towards the center. Hit the satellite and gets stuck. I can even ask a question like this. The rock is coming with speed v. Find v if the satellite escapes to infinity after collision. Meaning the satellite is coming and hitting with such a high speed, after collision, this thing will just escape to infinity. That also could be a way of asking. So there are different ways of asking the same thing. So let's keep it simple here. So find the maximum distance. I can even ask you minimum distance of satellite plus rock after collision. Think about this. What is happening, what and all. I'll give you a minute or two and then I'll explain, then I'll give you another minute or two. But I hope the question is clear. We have a satellite mass m going peacefully in an orbit of 3r with speed u. U can be found out. U is how much? Root over gm by 3r. That you can find actually. That is anyway given. Now we have a rock of half the mass and half the speed comes and collides radially, meaning this angle is 90 degrees. And get stuck. So E is 0. Remember, it's a perfectly inelastic collision, so energy is not conserved before and after collision. Try. 2 minutes. So, since it is a... Tell me one thing. After collision, you think it will still go in a circle? After collision, do you think this will still go in a circle? So when you collide here, this is the horizontal speed. It will collide like this. So it will get some velocity in this direction, right? And do you think it will still go in a circle? Now from here, it will start going in some kind of an elliptical orbit. Circle becomes an ellipse. You're getting that? It will start going in an elliptical orbit. So basically, this position which you have here, so you'll get actually two answers here. Huh? Basically, when I said this, when you actually, and again, remember the story. If you're not going in a circle or a straight line, then what you do? Energy and angular momentum. Story is still the same. So when you solve this, you'll actually get a quadratic. You'll get two roots. One will be the farthest and one will be the least distance. I didn't draw it properly. You getting it? So the initial distance need not be the minimum distance. Are you getting that? Because at minimum and maximum distance, the velocity is perpendicular to r, na? So do you think after collision, the velocity is perpendicular to 3r? It is not. So that is not the minimum distance. Is that clear, Vihan? Why that need not be the minimum distance?
Yes, sir.
Because for that to be minimum distance, and if it forms in, it should look something like this, isn't it?
Yes.
But after collision, the velocity is this way. I mean, this is not the ellipse. This is actually some kind of a, some ellipse, this is a part of it. So now what? So you can't conserve energy just before and just after collision, but just before and just after collision, the gravitational force is non-impulsive, so you can conserve linear momentum, isn't it? So linear momentum can be conserved just before and just after collision. So after the collision is over, then you can conserve energy. Are you getting it? After the rock sticks to the satellite, after losing all that energy, whatever is left, now that is conserved. So energy is conserved after collision. Energy is not conserved before and after collision. Now can you try? I hope you got an idea what I'm saying. Think, I'll give you 2 minutes, then I'll show you. So start with the conservation of linear momentum. Find the speeds just after collision. And just write the equations and leave it. Don't worry about simplifying it. The final quadratic is little messed up. It could be solved, but yeah. Let's see. This is just before collision. So just after collision, this kind of mass becomes 3m/2. It will get some velocity, let's say ux, and let's say this velocity is uy. There'll be two velocities there. Getting it? So there'll be a vertical component and a horizontal thing. So I can conserve horizontal momentum. So initially the horizontal momentum is m into u, and then it is 3m/2 ux. The ux is 2u/3. The vertical momentum is m/2, u/2 will be 3m/2 ui. The ui will be u/6. So there. So just after collision, these are the components. So ux will be 2u/3 and uy will be u/6. So this guy is not going in a circle. This guy will go somewhat like this at some angle. And be careful here. Energy is not conserved just before and after collision. Because E is equal to 0 to sticking. Is this clear, everyone? Then what? So this is the scenario there. So this distance was 3r. At this point, this guy is going with ux. This is going with uy6, and this is the velocity actually. So this thing starts going in an elliptical orbit. The farthest point will be this guy. Let the velocity be v, and this will be perpendicular distance, and this is r. I hope you remember that thing. Why the farthest point they should be perpendicular? Because if there's a velocity along the r bar, that means it is either getting closer or going away. It won't be the farthest point. And then you're done. If you're not going in a straight line, if you're not going in a circle, angular momentum and energy. So after the collision is over, you can conserve angular momentum and energy. So L1 is equal to L2. So initial angular momentum will be mass 3m/2. Remember, mass has become 3m/2. It won't matter, luckily it'll get cancelled. You take only the perpendicular component, so that will be 3m by 2 ux into 3r is equal to 3m by 2 v and r. So this is one equation. V into r is equal to 3r into ux, which is 2u by 3. Energy is conserved after collision. E1 is equal to E2. This guy will be half. Mass is 3m by 2. The speed is ux square plus uy square minus the energy is minus gm 3m by 2, and the distance is 3 gm by r. This will be half 3m by 2 v square minus gm 3m by 2 by smaller. If you substitute the values and solve, you'll actually get two roots, r1 and r2. The bigger one is the maximum distance and the smaller one is the minimum distance. Because there are two times when the velocity becomes perpendicular to the r bar, minimum and maximum. Clear with this? And if you see something about the question, you used conservation of linear momentum, you used conservation of angular momentum, you used conservation of energy. You used all the three conservations. Have a look at this. Clear? Great. See one more. Now, let's say we have a planet mass m and radius r. And let's say we have a satellite, it is going in a circular orbit. Mass m, and let's say distance is 2r, and it is going with some v. So now the thing about rocket engines, right? What happens? See, whenever you see a rocket, people don't just switch on the rocket and they just keep on using the fuel. It is actually a waste of thing. I mean, that is one way to do, but there's a better way of launching rockets into the space. So there is a difference. So whenever you want to launch something to Mars or something, what these people do, right? You don't switch on the rocket engines continuously. So what these people do, they switch on the rocket engine for a small time and then they switch it off. So they'll give it in bursts. So rocket engines work in small bursts, maybe few seconds when I say small. And every time the rocket engine switches on, what it gives you is an additional velocity. Remember, energy is not conserved. All that hot air and everything escapes out. So energy is not conserved when you switch on the rocket. So the rocket engine generates some kind of a thrust. It gives an additional velocity, delta v. So this comes from variable mass system. If you remember, the rocket ka thrust force is given by minus ur dm by dt. I hope you remember this. And if you see, this is a constant value because the relative velocity is constant. Dm by dt is something which you can control. So this will be force into delta t will be ur into dm, right? So this is nothing but change in momentum. This will be equal to f delta t. This will be delta p. So we get f delta t is equal to mass into delta v. Therefore, every time you switch on the rocket, f is constant. Time you can control. M is the mass of the rocket. So that is how your delta v comes. Is this making sense? So every time you switch on the rocket and switch it off, you gain this much speed. Clear? So Listen to the story now. So this is the thing what happens with the rocket. So this is how a paragraph will be. They'll explain something like this and so the rocket is going in a circle. Now you switched on the rocket at some position. So find the maximum distance. You can just write the equations and leave it. Find maximum distance from the planet. After the first burst. So after every burst, your speed becomes delta V more. So let's say the rocket started for small time and you got a speed of extra delta V. Now you won't go in a circle anymore. I hope by now you're clear with that, right? If something is going in a circle and you mess up the speed, you won't go in a circle anymore. So that's the first thing. Second thing. So after the first burst, so chalo, first time you started the engine wherever you want, it doesn't matter. It starts going in elliptical orbit. So after the first burst, at which point should you start the engine again to get maximum gain in energy? So it matters now. After the first burst, the second burst will matter, like at which point did you start the engine? That will give you either more energy or less energy. At which point engine should be switched on. To gain maximum energy. Third, find the minimum number of bursts. So how many times should I switch on and switch off the engine so that it can escape the planet? Let's get them all. So the whole story, right, is simply this. You're going with speed V. If I switch on the rocket and switch it off, your speed becomes V plus delta V. Simple. That's it. That is what it means. Now, luckily, when you're going in a circle, the speed is constant. But after the first burst, you start going in an ellipse, your speed is changing. So depending on when you switch on the rocket, you'll gain different amount of energies at different places. Let's see. Nasik, what happens here? So after the first burst, you are going in a circle. Let's say you switched on the engine here. Now, after the first burst, your speed has become V plus delta V. So you will start going in an elliptical orbit like this. And the thing is, you will come back to the same point, isn't it? It is a closed loop, so you have to come back to the same point. So now you're going in ellipse with speed V plus delta V. Getting it? And remember, this is the maximum speed for this orbit. Every time you come to that point, your speed will be V plus delta V. And this is the farthest point here. This will be your minimum speed. This will be V dash, and this will be the minimum speed. So your speed is not constant. Once you go into an elliptical orbit, your speed is continuously changing. Now the question is, after the first burst, now where should I start the second burst to gain more energy? Now, what is the gain in kinetic energy? So gain in kinetic energy will be half m. So after every burst, your speed becomes v plus delta v whole square minus your initial energy is half mv square. If I subtract this, you end up with v square will cancel. This will be mv delta v plus m into delta v square by 2. You can clearly see this term is constant and this term depends on speed here. So there, this is a catch here in this term. So we can clearly see here, if the rocket engines are switched on at maximum speed, you gain maximum energy. So you want to switch on the rockets every time you're having maximum speed. Switched on at maximum speed, we gain more energy. And simple math, na? Think about this. Let's say I can increase the number by 1. If your value is 50 and it increases by 1, so what is 51 square minus 50 square? If your value is 100 and if increase by 1, what is 101 square minus 100 square? The difference will be bigger when? The bigger the value, isn't it? 51 square minus 50 square is smaller compared to 101 square minus 100 square, even though they increased by 1 only. That is the second part of the question. So every time you boost it, you need to switch on the engine at that same point where you bursted the first time. That's what makes this thing very difficult. You have to have a very precise control. If you don't switch on the engine exactly during that time interval, then this orbit will start getting messed up again. So you'll start getting a different ellipse. You have to take care of all that control. So there's a very small time interval where you can switch on and switch it off. That's what makes it more complex. So if you try to solve this for the first part, this distance was r. This distance is r1. So I can conserve angular momentum. This will be m into v plus delta v into r is equal to m into v dash into small r. And then energy conservation after the engine was switched on, v plus delta v whole square. This is the standard stuff. Minus g mm by r is equal to minus g mm by r1. So I can put that and I can solve. So every time you switch on, your speed increases by delta v. So what to do the next time? So this is how the whole thing looks. So initially you're going in a circle. You switch on the engine here, so you're going with speed v. You switch on the rocket, your speed becomes v plus delta v. When you come to the same position, again switch on the rocket. Now your speed becomes v plus 2 delta v. Again switch on the rocket. Getting it? Again switch on the rocket, and so on. If you keep doing this, at some point you have gained so much velocity, it will be v plus n delta v. At this point, you will escape to infinity. So the energy becomes half m v plus n times delta v ka square minus g mm by r. That was the total energy. This is 2r. That distance is 2r. This value must be greater than or equal to 0 to escape, isn't it? So after every time switching on the engine there at that point, after n bursts or n times switching on the engine, you will gain enough speed. Your total energy becomes positive, means you have enough energy to escape the planet. Total energy becomes positive. So, so at the same point, the engine has to be switched on every time. So on paper, it looks easy. The biggest headache with this thing is the precise control. The advantage is you use very little amount of fuel. The disadvantage, this is going to take time. Correct? And every time you're switching on, you're increasing speed by 1, 1, 1, 1. So maybe this might take around 30, 40, 50 times. You have to do this and then it goes off. And this is how they actually launched a satellite to Mars. Mangalayan movie, right? This was the whole story actually. I explained even 3 pages in one question. They took 2.5 hours, but okay. That is because we know gravitation. So most of the audience don't know. So they had to give all kind of bullshit explanations and all. When I was seeing the movie, I thought this only bloody what are you guys even telling? Okay. Anyways, most of the people are not preparing for advance, so we can't expect them to know this stuff. But is this clear, everyone? So why switching on the engine at that point is the most important thing. And that is the reason why it becomes difficult as it goes faster and faster, isn't it? You have a very small time interval, isn't it? You have to precisely switch it on and precisely switch it off. Let's say by chance, accidentally, right? Instead of switching on there, you switch it on somewhere here, and then this guy will start going in a new orbit. So your whole calculations will keep getting messed up. You have to keep on adjusting the calculations. Because let's say at some point Mars is here, you want to launch in this position. But if this guy goes away to this infinity, we have a problem. So the problem was never the working and everything. It was always the control. Clear with this? And you can see what kind of questions we can do, right? All that I taught you is simple thing, this only, force and stuff. So today's class was very important. So please make sure to do all these questions again. This is how they ask questions. Take a break. Come back by 7, 6. We'll continue from here. Any doubt so far you can ask. Okay, come back in 10 minutes. Chalo, let's start off. Now, if you see that trajectory is actually, we don't have the proofs for this. We can actually use polar coordinates and the eccentricity to get this. So consider we second. So consider a particle is projected with speed u tangentially. Now remember, this is a very special case. Tangential to the surface. Case. So let's say projecting with speed u, where the speed u is less than v orbit. And remember, v orbital is root over gm by r. So then what happens? You'll actually go in an ellipse. And you will again collide on the planet only. You're getting it? Meaning this would be a smaller ellipse. And the center of the planet will be the focus. So the orbit will be an elliptical orbit. So what we studied in kinematics, right? The parabola thing, that is valid if the Earth was flat and the gravity was not changing, isn't it? If g is constant and the Earth was flat, it is actually a parabola. Here, g ka magnitude is changing, the direction is also changing. It actually forms an ellipse. Same thing if you go with speed u and let's say u is equal to v orbit. And this is the definition of orbital velocity. You start going in a circle. So tell me one thing. Suppose if I ask you a question like this, a particle is projected with v orbital from the surface, it will always go in a circle. True or false? A particle is projected with v orbital from the surface. It will always go in a circle. True or false? False, right? Because what if I project like this? Only if you project tangentially, you will go in a circle. So be careful with that. The third case, let's say again you projected it tangentially u, but this time the u is between v escape velocity and greater than v orbit. Then you will go in an ellipse, but this time it will be a big ellipse, something like this. So you'll get ellipse two times when your velocity is less than v orbit or between v orbit and v escape velocity. If you project with u equal to v escape velocity, this will be a parabola. This will go off to infinity. This is u greater than v escape velocity. It will become a hyperbola. Literally, you'll get your entire conic sections here. So the mathematical proof, right? You will get the eccentricity in terms of v orbit and v escape velocity. So for different values, you'll get different eccentricities. So based on that, you can prove like, which is circle, which is an ellipse and all. And we don't have that proof in our portion, so we'll not get into that. But you should know the orbits. So what velocity, how it will go. This itself would be a question at a mains or a bits level. So you can clearly see the parabola and hyperbola are not bounded orbits. They go to infinity. So basically, once you exceed escape velocity, you will go in a hyperbola or a parabola. Clear? Everyone? That's a bit about orbits, trajectories. Next thing, Kepler laws. Now, Kepler, right, is not actually a physics person. So the place where Kepler was living, there was an observatory. So and this thing had a lot of data for like almost like 130, 140 years. They had data for different planets, stars, and all that observations I have. So this guy went to the observatory, he started looking all this data. So he himself didn't actually do any observations or anything. You can think of he's more like a data scientist. He took out all the data there and he tried to see what matches and what is the pattern and everything. So based on the data, he postulated three laws. The first law, all planets revolve around the sun in elliptical orbits. Like I said, it doesn't have any proof for anything. It is just all matter of data there. With sun at one of the foci. I hope you remember the property of an ellipse. So if it is f1 and f2, there are two focuses. You choose any random point here, P. This is actually the locus, f1p plus f2p will be 2a. Hope you know this thing. You take any point in an ellipse and the sum of the distances from the two focus will be always constant. In the second postulate, area swept by the radius vector is equal in equal intervals of time. So this was a question in one of the exam, like, Kepler's second law is what? Meaning law of conservation of energy, law of conservation of linear momentum, law of conservation of mass, law of conservation of angular momentum. So this is based on law of conservation of angular momentum. So Kepler's second law is another form of law of conservation of angular momentum. This we actually proved. So what this thing says is, so let's say planet goes from here to here, A to B in time t. It goes from C to D in the same time t. So Kepler's second law says these two areas are equal. Area of SCD is equal to area of SAB. You can remember this. So the aerial velocity, that is the rate of change of area, the area covered per unit time, is L bar by 2m. And the angular momentum is constant about the sun. So this is the proof actually, the Kepler's second law. Now, like I said, this is an observation, but we can prove it. That's why this is based on law of conservation of angular momentum. Right, and the proof we did it in this question, this guy, page 70. Clear idea. The third law the time period is proportional to square of the time period is proportional to cube of the major axis. So t square is proportional to a cube. This is independent of minor axis. This is what I was saying. He just knows it is proportionality. He doesn't know the exact value. This also we proved there. So the actual formula is 2 pi root over gm a power 3 by 2. If you make a is equal to r, it becomes actually a circular orbit. Clear with this thing. That's your third law. And the best thing about this formula, you know what? Like I said last time also, did you ever realize how did you find the mass of sun? So if I know the time period of the earth around the sun, and if I can somehow find the distance, I can find that m is the mass of the sun. So this is how I actually find the mass of the planets or stars or something. You look at a satellite or a moon which is going around the planet, find the time period, and from there you can find the mass of the planet or the star. You do all indirect observations like this. Clear with this? There, these are three laws. Let's see some questions on this. So let's say this guy is going in a circular elliptical orbit. This is A, B, C, and D. This will be like mains level questions or a bits level one. So the question would be like this. So when this planet is going in its elliptical orbit, compare the time taken from ABC, not ABC, DAB, and compare a time DBCD. Which is greater, which is smaller, or they're equal? Compare the speeds, speed at A, speed at B, speed at C, and speed at D. Third, work done by gravity when you go from A to B, work done by gravity, B to C, C to A, and D to A. I just want you to tell me whether it is positive, negative, or zero. I don't want the value. So the question should be like this. If the planet goes in elliptical orbit from A to B, what is the work done by gravity? Is it positive, negative, or zero? There, these are like three simple questions I can ask you. Get them. I'll give you a minute or two. Let's see. Now, the most common mistake that people think, sir, BCD and ADB are looking equal areas. You're forgetting something. The area is not measured from the center. So the area is measured from the sun. So when you say DBC, we are talking about this area, isn't it? The area swept by the radius vector. And when you say you're going from D to B, we are looking at this area. Is that clear, everyone? So which is bigger? You can clearly see there. Area of SBCD is greater than area of SBD. Therefore, time taken to go from BCD is greater than time taken to go from DAB. Easy. Second thing, angular momentum is conserved. So the closer you are, the faster you go. The speed of VA is greater. B and D are symmetrical, and VC. Third thing, we know work done by all forces is change in kinetic energy. So if your speed is increasing, then work done is positive. If speed is decreasing, then work done is negative. So when you go from A to B, it is negative. Why? Speed decreases. Work done from B to C is also negative. Speed decreases. Work done from C to D is positive. Your speed increases. Work done from D to A is also positive. Speed increases. That's it. So if you know the speeds, you can even find the work done there. Clear, everyone? Any doubts on this? Clear, Nanch? Arya? Arnav? Clear with this? Niharika? Got it? Ahana? Puroja? Jainil? Sharman? Great. Next one. Let's see one more. So let's say, assume Earth is going in a circular orbit. Earth actually goes in a slight ellipse. This is another standard question. Now, hypothetically, let's say the Earth is stopped. Someone came and just caught the Earth and then they released it. If Earth is stopped and released, due to the gravitational force of Sun, the Earth falls into the Earth falls into the Sun. Meaning, think about it. So initially, what was happening as the Earth was going in a circle, the attraction force, which is G by R square, this is being balanced by your centrifugal force mv square by R. Now you're coming and telling me, for some reason, the Earth's velocity suddenly became 0. Now you can clearly see there's no one to balance that gravitational force. So then there's nothing there. It'll just go straight into the sun and collapse. Is that making sense, everyone? And time period for this thing is 365 days or 1 year, approximately. So the question is, so if you just stop the Earth and leave it, in how much time will the Earth go and fall into the sun? Find time taken for Earth to fall into the sun. Let's get this. I hope you're getting the question. So if you're going with some speed V, initially the centrifugal force balance is there, but if you suddenly leave it, you will just go straight into the sun and collapse. How long will that take? I hope the question is clear. Give it a try. Now, there's a way to do this, without any calculus or anything. You can just use a Kepler's third law and finish it off. Let's just listen to this. It's not tough once you know what to do. The thing is to get an idea. So initially you are going in a circle. Now, instead of suddenly making speed 0, just imagine a scenario where the speed is decreasing little by little. So when you go with speed v, you will go in a circle. So if you decrease the speed a little, as the speed decreases, it goes in an elliptical orbit. So let's say I decrease the speed a little, you will go in an ellipse like this. Let's say I decrease the speed little more, you will go in an ellipse like this. Now, if I put a situation where velocity almost tends to 0, this is the scenario where velocity v3 tends to 0. So if velocity v tends to 0, this will start becoming a straight line. Getting it? And orbit lives in an elliptical orbit, and length of the major axis decreases. So as v tends to 0, we get an ellipse. Right? Where b tends to 0. Basically, it becomes a line. You're getting it? Don't make exactly v0. If you put v0, it becomes a line. So you are saying it is still an ellipse with a, where b is tending to 0. And luckily, we know time period doesn't depend on b. So this is how the trajectory would look like. So if this was the sun, so initially you're going in this guy with some speed v. If you make v tending to 0, you get almost a line. So for this guy, the major axis is r. And for the blue one, the major axis is 2r. And we know the time period depends only on the major axis and independent of minor axis. So I can use that relation t square is equal to a cube. So I have t square by, let's say, t dash square is equal to this guy is r cube by r by 2 whole cube. So from here I'll get t dash will be t by 2 root 2. Now remember, this is the total time taken for the whole thing. This is for the full trip. But once you go into the sun, you're not going to come back. So for Earth to go into the sun, we need half of this. That will be t by 4 root 2. And this thing comes to approximately 65 days. No calculus, nothing. And you can also try this with integration, but yeah, this is much better and faster. You'll take let the distance be x, gmm by x square, and then mv square by r, and all that stuff, and then you can integrate. Clear with this, everyone? Yeah.
Sir, so it will be in an ellipse, right? So we decrease it by a small amount, it will take a round trip and come back in an ellipse. Decrease it by a small amount. So, sir,
Yeah, you're saying ellipse and ellipse, but God, this thing is going in ellipse about the center, right? So the ellipse would look like this. It will crash with the sun.
okay, yeah.
Is this clear, everyone? Getting the idea that so basically when you make v tending to 0, you can approximate it to be an ellipse. The line actually becomes an ellipse if v tends to 0. Clear with this? This is a pretty good mains level question. Right? These are the kind of questions which will repeat. So like these are easy ones. Let's see how they last this in advance. So we have a planet here. Mass m and radius r. This is A and this is B. Someone projected here with a speed of v, which is root gm by r, the orbital velocity. It goes and it lands at point B. So A is the pole. So someone launched a particle with orbital velocity from the pole. It went and landed on the equator. So there is some angle theta. We don't know. That is not given. But it is projected in such a way it is going and landing there. So projectile launched from A and lands at B. Find the time taken. So how much time will it take for it to go from A to B? It's a pretty good one. This will be a good advanced, maybe an integer question or a single choice question. This is the data. That's it. We don't have any more data. You are launching with the speed of root gm by r from the pole and you go and land on the equator. Mass of the planet is m and radius r. How much time will it take for this to go from A to B? I think it's little different, but now think of like this. When you see a question like this, I'll tell you what goes in my head. At least first time when I saw this question, right, long back, I said, okay, this thing looks pretty weird. What the hell? That is the first feeling you get normally. And then I thought, okay, can you tell me first of all, what kind of orbit is this? Ellipse, right? Itna to clear tha, right? Ellipse tha. And one thing I understood, there is no way you can integrate this. Elliptical orbits I can't integrate. I know I can conserve angular momentum, I can conserve energy and all. Great. I know this goes in elliptical orbit and you're asking for time taken. So now think about it. Elliptical orbit, time taken. The only time you studied about elliptical orbit and time taken was this guy, isn't it? The time period for an ellipse is the area of an ellipse by areal velocity, isn't it? This was the only time in your entire physics you studied the time period and ellipse together. So that gave me an idea. That means indirectly what he was trying to ask is, and can you tell me where will the focus of this ellipse? What is Kepler's first law? Kepler's first law says the planet will go in elliptical orbit with the sun at the one of the foci. That means the planet ka center is the focus. So indirectly what I'm asking is somehow if I can find this area and I know the areal velocity, my job is done, right? And how do you find the area for that? If I just draw a line like this, isn't this half ellipse? And that's one triangle. We need to prove there's an half ellipse. So that gave me an idea, boss. I need to find the area somehow. So once I got that, it is just a matter of figuring out that area and all. And then, yeah, you will, then it takes time, but you'll get it. But at least that's what it struck me in the beginning. Like, you know, this is what I'm saying. See, it can take more time to solve, but the idea should get it in at least 2 minutes. You should always think like that. What is given? Ellipse. What you're asking, time. It looks so weird. I have never found time taken for an ellipse till now, except in one case. So that is how you, that is what I mean by revision. Revision matlab ye nahi, you take a book and keep on reading, you should be able to relate stuff to the backward. Where did you see something like this? At least something like looking like this. And then from there you start. And if you think about it, right, this is how actually we learn anything. Whenever you try to learn anything new, you'll always try to see if there is any relation with what I'm going to learn with something similar somewhere. Just imagine you're learning swimming for the first time. When you're learning to swim, there is a thing. They will, when you're in the water, right, you have to move your legs like a cycling. If you do that up and down, you can go up and down actually. There's a thing like that. So the instructor might tell you like this, just like you ride a cycle, try to do that with your legs. Now, cycling has nothing to do with the swimming, but you can relate the stuff just for your understanding, and then you'll get an idea. Oh, like a cycle, how I do, you're also asking me to do the same thing in swimming. So you learn stuff like that. You don't learn anything completely new. Do you guys remember how did I teach you differentiation? If you guys remember the first differentiation, we started like this. I said there is a straight line. I found the slope. Then I said there is a curve. Then I said if I take 2 points and try to find the slope, it is meaningless. If I bring the 2 points closer, still meaningless. But if I bring the points very close, it becomes a tangent. So I started with a line and then I introduced the tangent, for a curve. And then I said this is differentiation and all that story. That is how you always learn. So keep that in mind. Not only physics, anything that you learn, you need to figure out with something you know. If you have no references before, you will not be able to understand. That is the reason it is very difficult to understand quantum mechanics. You can't relate anything in quantum mechanics, most of the stuff in quantum mechanics, with anything that you know in your life. So it feels really bizarre and weird. So it's like trying to imagine a hypercube, which is a 4-dimensional cube. We can never imagine. We humans can never imagine. We don't know what is a 4D. How does it even, it goes beyond us. But luckily, at least in 11th and 12th, when you're seeing a paper in advance, you know the question is something you can relate to. So you should be able to solve. How do we start? First thing, let's find the energy. So when you're projecting there, the energy of this thing is, first of all, I know this is an ellipse. So energy will be half mv square minus gmm by r. Substitute the values here, you end up with minus gmm by 2r. But I also know energy for an elliptical orbit is minus gmm by 2a. Therefore, we proved 2a is equal to 2r and a is equal to r. So we proved a is equal to r. So now if I take this ellipse, this is your focus. This is A, this is B. Think about it. If you say A is equal to R, this is R, and this is R, isn't it? This is possible only when it is exactly the minor axis, isn't it? Think about it. From the two focuses, this is R, isn't it? The sum must be equal. You tell me from the two focus, which point will be equidistant, the minor axis. Are you getting the logic? So that was a proof that this is actually a minor axis. So AB is minor axis. There are only 2 points on the ellipse which will be equidistant from both the focuses. I hope that is clear. And then you're done. So this guy will be how much? R root 2, which is 2b. I know A ka value, I know B ka value. And remember, what is the time period? Time period for an ellipse is 2 pi root over gm A power 3 by 2. A is equal to R. So this area will be pi AB by 2. this area will be r square by 2, half base into height. So for an area of pi AB, the time period is unitary method. For this area, pi AB by 2 plus r square by 2, the time is small t. So what is small t? Pi AB by pi AB by 2 plus r square by 2 into t. A is equal to r and B is equal to r by root 2. Substitute all the values, you'll get the answer. So the main thing is figuring out this part. If you had given any other velocity, right, this won't be an half ellipse, it would be something else. Is this thing clear, everyone? So once you got the area, it is done. It is because the aerial velocity is constant. The time period must be proportional to the amount of area. So from there, I can figure this out. If I substitute this, what do I get? Pi, r square will go off. This will be pi by root 2 by pi by 2 root 2 plus 1 by 2. Yeah, you can simplify this. You will get the answer. All clear with this? Now it looks, manageable. That is because you already know some data points, the energy of an elliptical orbit. You know the aerial velocity is constant. So if you know this thing, then it is fine. Is this clear, everyone? There. This is how they'll frame a question in advance. You can find the time for this thing. And one small theory is there. If you see the life cycle of a star, like how do these stars actually form? Just a basic thing. So know this because this could be a paragraph. They can always frame a paragraph and they can ask you. And this is interesting because it has multiple concepts in this. That's why I like this. So far, the basic theory that we have, right, how star formation, this is how we start with. We have these huge clouds of, hydrogen gas in space. We call them nebula. Now, where we got this and all that, we don't know. But these are huge clouds of hydrogen gas. When I say huge, you can't even imagine them. Like the entire solar system will be like small piece in front of this entire cloud. The entire solar system, like these are huge. Now, we don't know where these things came from, but they do exist. And these things have a lot of hydrogen atoms, and they're very far from each other, so we can the interaction energy is almost zero. But then what will happen? The gravitational force goes till infinity, so due to a very small attraction between them, the hydrogens will start accumulating together. So gravity is the thing which starts the whole thing. So due to the gravitational force, hydrogens come together. So they'll form a small clump. So you have a small gas ball. Now, once you have a gas ball, it will have some mass. If it has mass, more and more hydrogens will get attracted. So this actually becomes a self-reinforcing thing. The more mass you have, more gravity you have, more gravity you have, more gas you will attract. Eventually, as this goes on, at some point, this will reach a critical mass. Meaning the gas can still keep on accumulating, but something happens here. Now, as these things are coming closer and closer, the loss in gravitational potential energy should become something else. So this loss in gravitational potential energy becomes heat. So as more and more hydrogen starts accumulating, now what is the self energy for a solid sphere? Again, I'm approximating a lot of things. 3gm square by 5r. Initially, they're very far. Now they're getting closer. So it's a loss in potential energy, which is equal to ncv delta t. So temperature of the gas will start increasing. So this ball will start gaining temperature. So initially, it was something like 0 Kelvin. They're very far from each other, and the gas molecules are almost stationary. So this ball ka temperature starts rising. So temperature T will be 3gm square by 5r ncv. N is the number of moles, so there's one mass ka term there. So the temperature keeps rising. So more and more mass you get, more and more temperature you get. Great. So what? If you get more and more temperature, these hydrogen molecules will start gaining some kinetic energy, which is given by 3 by 2 kT. K is the Boltzmann constant. Thermodynamics, everyone. And these molecules now are moving rapidly and they're colliding with each other. Now, if you look at the hydrogen nucleus, both are positive charge. They repel each other. So whenever they come closer, they repel and fly off. But if you bring them very close, if R becomes less than 10 power minus 15 meters, basically this is 1 Fermi, something happens. Nuclear force comes into picture. So nuclear force is a force between the protons and the neutrons. Did you ever think about this? In school, we studied in oxygen atom, there are 8 protons and 8 neutrons. And we also studied in school, the protons, right, like charges repel each other. So did you ever think about it, how in such a small nucleus, 8 positive charges can stay without flying off? Logic hai na? Socho na. If you take a sodium nucleus, it has 11 protons. All are sitting in a small space. And if we know protons will repel each other, so technically they should fly away. But they're not flying away. Means there is someone else whom we don't know who's keeping them together. That is how you conclude, right? Technically you should fly away, but you're not flying away. So people found out there's something called a nuclear force, which is very highly attractive. But for this to act, the distance has to be very small. We will talk about that in modern physics a bit again. The nuclear force will start acting. And this is an attractive force. And this is very strong. This is so strong, it can even overcome that repulsions between protons. That is when nuclear fusion starts. So if you can bring the distance this close, the hydrogen will fuse, will start getting helium. That is how a star forms. That is what is happening in our sun. Hydrogen combines to form helium. So this hydrogen will come with some kinetic energy, and this hydrogen will come with some kinetic energy. Initially, let's say they're very far. So you need to bring them to a distance of 1 Fermi. And then they will combine to form an helium. Again, I'm skipping a lot of steps. There are multiple steps that will happen, but you'll get a nuclear fusion. This releases even more energy and you get more temperature. Star becomes even more hot. So all this kinetic energy, right? The loss in kinetic energy becomes gain in electrostatic potential energy. Did you see what happened? Gravity became heat, heat became kinetic, kinetic became electrostatic. And that's why this thing is a pretty good one. There's a possibility of some time they can ask you this anytime. So this guy will become 3 by 2 kT 2 times because there are 2 of them. This will be K E square by R. So from here, if you substitute the Tika value, you will get the critical mass. So for a star to form, there should be a certain amount of mass that should accumulate. So if you don't have enough mass, you won't get a star. So you can say Jupiter is an incomplete star. So when the stars are forming, as the mass is accumulating, at some point, let's say it is not able to accumulate more mass, it just remains a gas planet. So if you can pump enough mass into the Jupiter, it will start and ignite and become a star. This is how stars form. The more mass you have, more temperature you have, then helium also can collide and they can form higher elements. So the hotter the star, the higher the elements. Sun is a very, meaning if you put an exam among all the stars, Sun will get around 15 marks out of 100. It's a failure. That is the reason Earth maybe have life. So Sun is not really a hot star. It is pretty chilled out one. So we have stars which are huge. The temperatures are unbelievable temperatures. Things are like 1 lakh times hotter than Sun. So these things, right, they even form much higher elements, but there is a problem. The elements will form up to iron and then they stop. The reactions become endothermic after iron. Again, we will talk about that in modern physics. So any star cannot exceed more than iron. So they form till iron and then stop. But we know on Earth, we have elements greater than iron, right? Zinc, copper, gold. So these things cannot form in a nuclear fusion. So something else happens. So after the star forms, And as the fuel is burning out, when you say the fusion is going on, at some point the fuel gets exhausted. Yeah, I'm giving a very simplified version of it. So the star, what will happen once it fuel gets exhausted, it starts cooling down, the star will start shrinking. Once the star starts shrinking, the inner layers will get compressed and the inner layers will undergo fusion. The temperature rises to very high and the inner layers undergo fusion. Basically, they'll form next higher elements. And now this thing will start expanding from inside. The star becomes huge. We call it a red giant. This will take another, I think, 200 or 300 million years for the sun to become a red giant. And when it becomes a red giant, it becomes so huge, it will eat away Mercury and get very close to Venus. It becomes that huge. And after it becomes a red giant, at some point, it explodes. Exactly why, we have no idea, but it does. There are some explanations are that this thing just explodes. And when it explodes, two things happen. The material gets pushed away. This is called explosion. So this matter will fly into space. The other thing, this matter also will get pushed inside. So it will also, this is called implosion. The force is so high, it will get pushed inside, it will get pushed outside both the directions. So this implosion is so violent and so strong, the elements are forcefully combined. So all the elements greater than iron are formed during an implosion, during a supernova explosion. At least this is the theory so far we have. So all elements greater than iron form in during this thing. So every element greater than iron, you can see it is formed in a start, basically a supernova explosion. Greater than iron, they form here. And after this, some part of the mass is left out. Now, whatever is left out, if this mass is greater than 1.5 times solar mass, if we take the entire solar system ka mass, and after explosion, whatever is left out, the gravity is so strong, the electrons will fall into the nucleus. And this thing becomes a neutron star. It becomes very dense. But let's say the mass is not 1.5, but the mass is greater than 3 times solar mass. The collapse won't stop. The gravity is so strong, it won't stop at the neutron star. It will still further collapse into itself, and you get a singularity, a black hole. And at that point, the entire science, physics, whatever we learned, everything breaks down. We don't know what happens after that. Stories end there. So people do say black holes also eventually evaporate and they vanish, but yeah, we really don't have much of a knowledge about this. So this is what happens with a full thing. So this is how stars form and this is how they get destroyed. If you don't have enough mass, you will be just left out like this. Okay with this? There. So this is just like a small story there. So have an idea, because these are the kind of things you can get in a paragraph. They'll explain you something and they'll ask you some stuff. There. So that is about it. So with that, we're done with the chapter gravitation. You saw especially the satellites part is quite different from electrostatics. We didn't have anything like this. So make sure to go to this, especially today's class, if you see we really had some really good problems. So make sure to revise once and start solving this. Next class, when we catch up, we'll start off with Gauss laws. So that is also based on electrostatics. Chapter is not tough, but the problem with that, right? The numericals are a little weird.